Hi, Dr. Manavendra.
Good morning. Good morning.
Yeah, I think good morning. Yeah, still 2 minutes
Today is
to
the
go.
today is
Yeah,
the last day. So yeah.
this is the last day.
Yeah. So, can you just allow me to share screen so that I can check?
Yes. So co-host, yes, Karan, can you please allow our
Hi,
speaker
Vijay.
to?
How?
Hi, hi. How are you? Fine. Nice to meet you.
Yeah. So everything
Yeah.
okay in IIT Madras?
Yeah, it's okay. A number of students' cases are increasing these days.
Okay, yeah, same
Well,
here.
that's everywhere. We have
Yeah.
faculty also.
Yeah.
By the way, we are on YouTube.
Okay,
So
okay. Sorry.
just Karan, yeah. So now the screen share is allowed.
Okay.
Can you please check?
So is it okay?
Yeah. Yeah. It's not
Yeah.
full screen though, but yeah, the
Yeah.
sharing part is fine.
So it is now full
Yeah.
screen. Yeah.
Now it's full screen.
Okay. I think this title.
Okay. So maybe we go towards the start.
Yeah.
So, welcome everyone to the sixth day as well as the last day of our conference QFTA 2020. So, I am Manabendranath Pera. I shall be chairing the first session of the day. And our first speaker is Professor Bijoy Krishnadas. And let me take the privilege to introduce him. Dr. Bijay Krishnadas obtained his PhD degree in integrated optics from the University of Paderborn, Germany in 2003. Dr. Das started his research career in the area of photonics at the Microelectronics Center, IIT Kharagpur, nearly two decades ago, when he was associated in a DRDO sponsored project. Since August 2006, he has been associated with the Department of Electrical Engineering, IIT Madras, Chennai, India, where he is currently holding a full professor position. His research focus is silicon photonics devices and circuits, in particular, optical interconnect and quantum optics applications, integrated RF photonics signal processing, lab on chip biomedical applications. So today he will be talking on silicon microring resonators for nonlinear and quantum photonic applications. So with this, I would like to request Professor Vijay Krishna Das to start the seminar. Over to you, Professor Das. Thank you.
Yeah. So thank you very much, Dr. Bera. and uh, thanks. I'm really grateful to the organizer for giving me opportunity to present our work on silicon photonics, particularly for quantum photonic applications. We have started a couple of years ago, and we progressed a bit. And I think this is a very good platform to share our work. And we are, of course, we are very preliminary stage as far as experimental related work on quantum photonics, but we are very close and we are getting good results. to go to the next phase. So it is really honored to share our work in front of this experienced audience, and very much interested to get feedback from the audience. And I would not mind if you stop me and ask me questions. If anything not clear very much, I would be happy to answer. And yeah, as Dr. Bera says that my today's talk is electrically controlled, a little bit changed title just to make more um, uh, emphasize on the content of the talk. So electrically controlled optical bistability in silicon microring resonator for quantum photonics applications. So as you go through the talk outline, I have just, there are 5 points, bullet points I mentioned. So, you know, quantum photonics technology, there are various platforms, various materials, various ways, various device people are projecting and demonstrating for different applications. So I would be discussing a little bit on a certain platform called Silicon Photonics platform. Why this is so much important for quantum photonics applications. First of all, just 1 or 2 slides I'll be discussing on that, just a couple of minutes. And then I'll be just discussing that's a silicon microring resonator, actually long time known for, it's a very good efficient photon source. And people already demonstrated, some application also demonstrated on chip applications. But while giving such very good results, while investigating, we find that there is a really serious bottleneck for silicon microring resonator. Due to some reasons and many people not reporting that, we recently found that serious bottleneck because of the bistability. And we also gave some solutions how to overcome that bistability, because optical bistability is known, but no one reported so far that this optical bistability could actually hamper the efficient photons generation, stability point of view as well as efficiency point of view. That is a big problem, and we came out with a solution, and we'll be discussing that. And yeah, so we, after this solutions, we also the theoretical development, everything we did, and then we designed a device and fabricated, and we have seen that really it is much more stable and efficient for Fourier mixing process. You see, Fourier mixing process is you know, that is actually used for your photon pair generation. Particularly spontaneous Fourier mixing process is used for spontaneous for entangled photon pair generation, as well as heralded single photon for different applications. So we demonstrated this Fourier mixing process. Of course, because of the, we don't have single photon detector in our lab, but we demonstrated with a stimulated Fourier mixing process, and we have observed that what could be the generation rate. We could extract that as per whatever people are reporting, and that is quite stable. And then I will be just discussing about summary and conclusions. So these are our, we are experimental group. We have been working for in silicon photonics for last 15 years, and developing silicon photonics technology, design devices, fundamental components, etc. And very recently, we, as I said, that we are going for quantum photonic applications. So far, we say that there are 14 research scholars are involved. Out of them, 10 are PhD students. And I'll be talking today mostly the work of Riddhi Nandi, who is actually writing her thesis now, and also Arnab Goswami, this 2 senior PhD students. Their work I'll be highlighting today. Okay, so a little bit of introduction. So maybe many of you may not be knowing why silicon photonics so much important. Those who knows, I think for them I just take apology for just bear with me for this slide. And for those who don't know, they might be thinking that why quantum photonics in silicon substrate, why not whatever quantum computers, etc. people demonstrated the superconducting and other platforms, why it is so much important, why people are working on this area. I just want to explain. So first of all, if you say silicon photonics, actually industry started exploring about 20 years ago. Silicon photonics technology, because you know silicon is very good for CMOS electronics, and photonics, optical devices or integrated photonics could not be demonstrated before 2000 because of the quality. Although electronic grade silicon substrate crystals were available, but optical grade silicon substrate crystals were not available, and about almost 20 years of research, then it was proven that, okay, silicon photonics, you can fabricate integrated optical devices, including modulator, detectors, and in some way, some laser sources, etc. Then industry came in and they started exploring how this silicon photonics, because it is silicon, and then you can actually integrate both electronics as well as photonics. So whatever the bottleneck comes from the electronics, that can be particularly interconnect bottleneck, that can be solved by replacing electrical interconnect with optical interconnects. So in this way, Intel's and Luxtera, many companies, semiconductor giants, they started developing product in 2000. And just one example, Intel took about 16 years to demonstrate its first product, that is 100 Gbps transceiver. And almost same time, Luxtera, fabless company, started working on that. Now, I think a couple of years ago, that has been bought by Cisco, and they also have 400 Gbps transceiver. So that is the huge market so far in the as far as silicon photonics is concerned, and about currently it is almost about 1 billion market, and they are basically being used in what you call that, data centers. So by 2025, it will become about 3 billion market. So why this is so much growing, if, considering other integrated photonics platform? Because silicon photonics, not only you can integrate electronics, you can also use existing foundry setup, just a little bit modification or known PDK process, fab process, etc. You can just extend that one for silicon photonics devices and interconnect. And that is how cost wise and efficiency wise, it is much more better. And that's why industrial success came in. And today, after you see, this now only products, mostly these products are available. But as far as research goes on, it has been found that this technology can be extended to many other applications. In fact, it has been actually proven that it is going to be a disruptive technology for 21st century for all sorts of applications, starting from quantum logic gates, optical interconnects, that is what I mentioned, reconfigurable, that is high-speed transceiver also I mentioned, and then advanced civil radar, that is for microwave photonics technology, lab on chip, medical applications, that means what you call that, level 3 sensing, etc., neural network, artificial intelligence, and of course 5G communication, 6G communication, all those type of things people are projecting. And among them, one of the interesting thing people are trying, that quantum photonics integrated circuit, because it is silicon. If you can implement, if you can demonstrate some quantum photonic component on chip, then you can actually, you can scale it up. You can actually, a large number of qubit you can generate, and you can manipulate, you can get all sorts of quantum, particularly linear optical quantum computations, as well as QKD chip for secure communications. All of you know that because this conference is for that. And I want to just discuss here, if it is so, if technology available, and the waveguides, interferometers, and photon sources, everything can be demonstrated, the device can be developed, designed, and fabricated, then Still, why it is not progressing in a faster way? I want to explain here that there are little bit of hiccups are there, some hinges are there, some problems are there that will be discussed first, and then that will make us relevant for our next course of explanation. So if you see, this is a just kind of artistic scheme, actually just a kind of what cartoon. It is shown that you have to have some kind of photon source, and that photon source in principle standalone way it has been demonstrated with silicon waveguide. And then once you get a photon source, entangled photon pair, and also you can get heralded single photon by multiplexing, demultiplexing you can get. And then you can have different type of filters just to get high quality fidelity of the generated photons. And then you have all sorts of interferometers that actually needed for developing or demonstrating unitary matrices for quantum computation or quantum interference and so and so. That thing needed. And then you need a, of course, a single photon or qubit detection system, single photon detectors needed on chip. And then, of course, it is silicon, electronics can be done. Control electronics, feedback electronics, everything can be done. So, you know, this control electronics point of view, it is fantastic, it is good. And photon source also, it can be demonstrated, it has been shown. And magenta interferometer, phase shifters, modulators, all those type of thing, actually, you can directly borrow whatever demonstrated in transceiver technology. Same technology, same PDK you can use, and you can demonstrate everything. You can design accordingly all the components. One of the major bottleneck is that this thing, I'll just discuss that this pump removal filters. So you need a four-way mixing process for photon as a photon source, but residual pump, if it is there, it is guiding throughout, then it will create not only some noise also, and it will also make problem for your detection of your all the qubits and quantum states. So that is one problem. So this pump removal filters, you need very high extinction pump removal filter. You need at least 100 dB. Then only you can actually reveal your generated photon, because it is actually Chi3 process in silicon, and that is very weak, and brightness is not that great, whatever generated photon. So pump has to be suppressed, and then only you can get a very good source. Okay. And then another thing is that single photon detector, you know, in silicon, normally you have to use 1550 nanometer wavelength, and high efficiency detector at 1550 nanometer single photon detector means superconducting detector, SNSPD. So that you have to operate at very low temperature, and that if you are integrating here on chip, then you have to put entire chip in superconducting temperatures. Though the photon source for generating photon, you don't need to have low temperature. You can operate it at low room temperature. It is unlike your quantum dots or any other type of single photon sources. So this is good part here. But this single photon detector integration on chip, if you do, then you have to do low temperature. So people are working so to get some kind of SPAD, SP, so-called single photon avalanche detector, high efficiency detector, so that you can work on it. Some demonstrations are there, but it has to be improved. That is one bottleneck still there. Okay, so these are the two bottlenecks currently people are facing. Once it is done, then you can actually scale up like anything, because it is just semiconductor technology. Okay, so now instead of this this photon source, initially people demonstrated with a long waveguide to enhance the nonlinear interactions. Okay, and but people also try to explore a ring resonator, ring cavity, this type of thing, where actually you can launch your laser light, and because of the resonance, field can be enhanced, and then nonlinear strength can be increased, and then you can get a photon out, entangled photon pair out, and you can extract. So this ring resonator not only used for as a photon source, but also it can be useful for pump rejection if you just cascade several rings. So higher order filters can be demonstrated, and in principle you can get people reported very large extinction filter, but not reproducibility not so good. So we are also working in that front, but today we will be talking about how this ring resonator is useful for entangled photon source and what is the problem and how to solve. Okay, so this is a little bit of extended version of that one. Here we have just shown that filter, whatever the desired features you need. Normally we are working as a DBR structure. We could reach up to 65 dB extinction, but we need to go up to 100 dB, then it would be good. I think we need to cascade or redesign our DBR structure. We are working on that. Our theoretical result says that you can get more than 100 dB, but experimental results, we are getting up to 65 or close to 70 dB, because there are a lot of forward coherent scatterings happening. So that type of scattering has to be reduced by better designing of the DBR structure. And spiral waveguide, if you just replace like this ring, then what happens? Because of the Chi3 process, you get signal and idler at two different frequencies, just maintaining energy conservation. Two pump photons will be utilized, then signal and idler photons will be generated, and momentum conservation, everything happens. And then if you see that if it is a ring, normally this if pump is resonant to a pump is matched to a pump wavelength is matched to a resonant, then signal and idler, they will be matched to just neighboring resonance, and they are more or less their momentum also will be matched. Phase matching condition is inherent if only if the waveguides are not so dispersive. So you can design a waveguide where dispersion is low, then you can actually pump, your pump laser can be resonant to a particular, match to a particular resonant wavelength. For example, it is shown here. Then what happens? Signal and idler will be generated here at these resonances. So these are the resonances. In transmission, it is shown here, transmission characteristics shown here. It's a experimental results. So if you just match your pump wavelength here, then signal and idler correlated photons will be generated. Not only these two, if a pump strength is sufficiently high, then you can get also correlated photons here also, other things. They will be energy matched, and energy conservation will be there, as well as momentum conservation will be there. And if you try to see for a CW pumping, CW or maybe pulsed or whatever pulse case, average case, then your generation rate, that means this, because I said that this is a Chi3 process, and silicon of course is not Chi2 process is absent. So you have to exploit the Chi3 process. That is what for a mixing. And then generation rate expression, it is actually look like this. If you just do a little bit of nonlinear classically, you just semi-classically, you just derive, do little work, maths, then you get this expression where you see this 8, this numerical number, Vg is the group index, and gamma is the, that's a nonlinear coefficient. And then Pp is the pump, launched pump into the ring. And Q to the power 7 is the overall quality factor of the ring. And omega r is the resonance frequency, r is the radius, and this QE is the when that is one type, another type of quality factor for external. That means if you are considering ring resonator as lossless, then this, because of this coupling, whatever the ring quality factor comes, that actually you can use. So this is the generation rate. But this generation rate, it covers for the entire bandwidth here. You know, this is the entire band, because resonance has a bandwidth. That's why it is important to have another figure of merit called brightness. So that brightness is a number of whatever the generation rate is happening, you just normalize it to pump power as well as normalize to bandwidth. So that per frequency, per wavelength, how much it is generated. So that will be like this. So this is this actually reflects that gamma is a constant for a silicon. Vg depends on your waveguide dimension, and then radius is very important. Smaller the radius, so your brightness will be higher. That is one thing. And of course, pump more, you pump, you get brightness more. And Q value, of course, losses, etc. if you can reduce. So these are the parameters while designing your ring resonator for photon source. So you have to take care of all these things. Okay. So now one reported result that is just 2018 from silicon ring resonator. It's a very nice work. But if you see that this is something pump and this you amplify, then band pass filter, attenuator according to your requirement, you can pump use and then couple to the ring. And then you can use some kind of demultiplexer array waveguide grating so that you can split your signal and idler, and then you can just measure the correlation function, particularly second order correlation function G2. And they measured the G2 as a function of pump power. If you see that G2 0, that is very important whether you are getting a really single photon source, or you can separate as a single photon, or you can use as a heralded single photon. Then you see that G2 0 as a function of power, because expression says that as a function of power, your generation rate will be increasing. So as you increase the power, the G2 will be increasing basically. That is actually unwanted. So G2 smaller the G2 0 is better. So some noise is there. So where from this noise coming? Of course, pump power increasing, the probability will be increasing. You need to use a smaller power so that you can get G2 0 as small as possible. But in spite of that, they could not demonstrate that G2 0 could be 0. So it's not like a completely anti-bunch type of photon generation is happening. So this thing attributed to many problems basically. One major problem, as I said, that this optical bistability. So optical bistability, whenever you are pumping for a pump wavelength resonance to match certain point, you keep the resonance wavelength the close proximity of a resonance. Then if you just keep on increasing your pump power, then you see that the output power goes like this and drops because of the resonance, and then it goes like this. And while return back, it shows like a hysteresis. So this type of, so this is kind of optical bistability, and that bistability arises because of the different type of mechanisms we studied. That you know, whenever you are pumping, field strength is increasing in the ring, and because of the higher field strength, you get free carrier generation, and free carrier can also introduce some losses and free carrier dispersion. And also free carrier also dispersion can give you delta N, and also free carrier can recombine, generate heat, and that will give you thermo-optic effect. And apart from that, you have Carr effect also. N2 parameter is there, so refractive index will be changing. So because of that, this bistability is there. And we have seen that type of bistability in our fabricated, this is one of the ring resonator fabricated at IIT Madras. And we found that because of the bistability, that apart from that type of characteristics shown here, this characteristics here, we see that as you increase the pump power and you scan the resonance, then you see that resonance is actually changing and shape is also changing. That is actually because of the bistability. Okay, sorry for that. And this wavelength shift, everything is happening because of that. And so we thought that this is happening because of the phase change, nonlinear phase change happening. So nonlinear phase change, I think all the things, all the physics we studied and we have simulated, and then we found that if you can control this additional phase change by external applied phase, then you can actually control the bistability, and you can actually maintain the field inside field stable, as well as nonlinear phase can be compensated automatically by feedback control loop. So some of the device we fabricated here, this ring resonators, and then this micro heater is fabricated so that you can actually apply some heat through micro heater because of the Joule heating effect. And then you can introduce via thermo-optic effect some kind of phase. So 3 different micro heaters we tested, we characterized, and this is your waveguide, and this is micro heater. Just pass current, and then you hit the waveguide, and so refractive index change. So here, I think one of these device showing such a result. All the devices almost similar results. We have used this type of experimental setup. What we find that You see, you keep a, for example, this is your transmission characteristics, and keep your pump wavelength somewhere here, close to the resonance. So you are putting right side because as you increase your pump, that heat will be generated bit, then it will be rate shifted. So it will be, there is a chance that this pump wavelength will be matched to the ring resonator, resonance wavelength. So if you increase the bias voltage here, then what you see in the forward direction, this black curve you follow, it goes like this transmission, and minimum transmission is like coming here. That is actually minimum transmission coming means you are ensuring that it is actually matched to resonance. Your wavelength, whatever wavelength you have given, that is matched to wavelength, and it is going this way. And when you are reducing your bias, then it is cooling down, and what you see another interesting type of hysteresis, not like a power type of hysteresis, and you see it is dropping at some other bias voltage. So, and extinction is very high. So extinction is very high means here internal field strength is very high. Okay, so that means I can control the bias and keep fixed at this point, so that inside the ring you can actually enhance the field strength. In that case, you don't need to change your wavelength of the pump laser. Just any pump wavelength, you just change the bias, then you can control. And if there is a little bit drift is there, you can have a feedback control. You can just control that. Okay. So this also matches to our simulation result, experimental result, and simulation result matched, and how much lambda shift also happening, that also matching to our experimental results. So this is the results for stimulated Fourier mixing process. So what we did, we could program to operate our ring resonator at this point or B point, point A or operating point B. So you can make some kind of program so that you can bias your device for a certain bias point. Then you see for a pump here, this is your pump wavelength, and this pump wavelength you are pumping, it's coming out of ring resonator also, even though it is resonance, this much value is coming. And then you have signal and idler, signal and idler is generated. And also you could see also some kind of conjugate idler is generating. So that means in this case also, of course, what we did, that this is stimulated Fourier mixing. We have used idler. That is how we get so much value. Otherwise, the generation rate only for spontaneous Fourier mixing process, which is actually required for your photon pair generation. That is actually quantum photonic process. But we have used stimulated photon emission. Of course, we evaluated for this type of gain, how much generation rate is there. It is matching to our theoretical results explained earlier. Okay, so this is shown here. So this is actually taken when it is operated at A. But if you see, this is about minus 46 dBm. But when you are operating at B, then you see this gain is increased, at least 10 dB, 11 dB improved. And we could actually stabilize here, and we could demonstrate all these stimulated for a mixing process. And we have also shown that what is the field strength corresponding Q value you are getting, that is matching to our theoretical results. Okay. So with this, I just almost close to our summary. And this is actually, we have explained detailed theory of optical bistability, and then Carr effect, TPA, FCA, FCD, FTPM, thermoptic phase shifting, everything considered. So some of the effects are rate shifting and some of the effects are blue shifted. We just adjust. Some of their values are very fast and some of them are slower, everything considered. And then we find that the phase dependent bistability, that is our new thing. We could actually integrate a micro heater to control the bistability of the ring resonator for the first time, and demonstrated a stable stimulated Fourier mixing process, and ensuring that this would be a very good stable quantum photonic source. That's photon source ring resonator can be useful, programmable, of course. And this particular micro heater, we have demonstrated up to 45,000 Q values. But some of our device with a different design, because sometimes you need to design your waveguide so that dispersion is as minimum as possible. In that case, Q value is slightly lower, so Q value can also increase. and also you can switch. For example, if you want to have your photon source like a pulse type things, instead of pulse palm pleasure, you can use CW, and then you can switch your bias, and then you can actually control your what you call that, ring resonate photon generation rate, and you can get the photon generation window. And then stimulated for a mixing process demonstrated. And yeah, so we must acknowledge that. I think yeah, cost program of DST. I think I should mention also a Netra program from the MAITI also for funding for all these things. And we are very much close to our devices working reproducibly, and we could not demonstrate this all this G2 everything and for complicated structure because of the lack of SNSPD things there. We will be getting soon, and we will hope in some other meeting we will be able to present. With this, I just thank you once again for your patience, and if you have some questions, I can take if time is there.
Thank you very much, Professor Das, for a very clear presentation. We enjoyed very much. So now the house is open for question. So now I request to the audience, if you have some question, please raise your hand, or you can also write your question on the chat box. So if you have some question, please raise your hand. Yeah. I still don't see any hand raised. So
Okay.
I have one, maybe because I'm not really an expert in this field. So I have some more general question to ask. So in general, when you say that you have on-chip these optical devices, so how do you do the measurement? For example, if I want to have non-local measurements, for example, entangled basis and etc., how you do in this kind of chips?
So measurement, this detection is outside. So as far as
Okay.
so all
Okay.
you have to have your SNSPD. That is what we are waiting for to come. So all the measurements are happening outside. You have to take outside,
Okay.
but in all the operations, generation operations, all the unitary operations, etc., you can do on chip. All the components you can do on chip.
Okay.
Detection is outside so far. That is what I just mentioned that in the past. That is we are waiting to develop someone to demonstrate very good quality detectors also. You see here, this single photon detectors on chip. That is also research going on. If it is coming, then it will be for that. So then you can do on chip measurement, everything.
Okay, okay, okay. And what about the scalability, for example? Because in general, this, for example,
see, scalability, I think you cannot expect the scalability similar to electronics technology, because their transistor size is coming down to 5 nanometer, less than that atomic scale. And but here your scalability depends on how small your ring resonator you are fabricating for photon source, and Mach Zehnder interferometer is also a little bit larger. And so all those type of things, their scalability, at least people demonstrated so far about thousands of components together. I think up to 4 qubit generation people demonstrated. So I think for all these operations, I think 4 qubit is also good enough for that thing. But it can be scaled up. Depends on your capability of your foundry. So that bigger device and that can be done. And only thing is that you need you need really a programmable chip. So that you if you are making thousands of components, you need thousands of phase shifters. All the thousands of phase shifters, you cannot just switch on at one go. You have to just you have to program that, okay, this set of phase shifter I need to switch on now for all the unitary operations. So another research going on, depends on how good your you can do the programming, and crosstalks you can eliminate depending on that. Right now people are in 2 qubit, 4 qubit, up to 4 qubit level. Yeah.
Okay, okay, okay. Okay, thank you. So we have one question on the chat box.
Yeah.
Dr. Rajiv, can you please unmute yourself and pose the question directly? Yes, please. Rajiv, we cannot hear your voice. Yeah. I think he's trying to speak, but there is a noise.
Yeah.
Yeah,
Say
Rajiv, please.
Rajiv. Yeah.
We cannot hear you, Rajiv.
How about now?
Yeah.
Yes, yes.
Okay,
Please, go
great.
ahead.
Thanks for such a nice talk.
Thank you.
I was just wondering if you have thought about generating, let's say, single mode squeezed vacuum on your platform.
Yeah, I think that thing we have not explored. I think maybe we can look for it. Right now, we are interested on just up to car measurement, G2 zero measurement, all those type of things. That is what I think squeezed. I think some reports are there, but yeah, that would be another area to explore. Yeah, true. We have not done yet. Yeah.
So I guess for that, you don't really need an SNSPD. You
Yeah,
could
sure,
just
sure. Yeah,
right.
sure.
So if you have to do that, what do you think would be the main limitation? Is it the
I actually I can't answer at this point of time because we have not explored that one how it will work in silicon. Mostly people are demonstrating with this correlated photon pairs, etc. So I think that part we have not explored. I've not seen many papers also on that. I think one or two paper I have seen, but yeah, I have some limitation on that actually to comment on.
Yeah, thank you. I actually have another follow-up question.
Yeah.
So I was just wondering,
Yes,
what is
please go ahead.
your off-coupling loss when you go from
Yeah.
chip to the free space?
Yeah, coupling loss is there. This is loss actually one of the major problem for silicon photonics. So per facet it is about 6 dB loss at this
6
point of
dB,
time,
okay.
6 dB. But there are high level design available. People can reduce that. But I think with 6 dB is also good enough if you have a amplified. I think if it is a ring resonator, it is a 1 milliwatt level. If you can launch, and then you can generate your sufficient number of photons. Sufficient rate you can get.
Okay. Yeah. Thank you.
Thank you. Thank you.
Thank you very much, Rajbir. So since there is no more question coming from the audience, herewith I would like to thank Professor Vijay Krishna Das once again for this interesting talk and also the discussion.
Thank you very much.
And thank you very much. And with this, we'll go towards our next talk of the session. And our next speaker is Dr. Rajbir Nehra. Let me introduce him quickly. Dr. Rajbir is currently a postdoctoral scholar working in photonics quantum information processing at Caltech, Pasadena, USA. He received his PhD in atomic and molecular physics from the University of Virginia, USA. And just to mention also, he has been an integrated BSMS student from Indian Institute of Science, Education and Research, ISAR, Mohali, India. So today he will be talking on towards universal quantum computation with optics, new tools for quantum state tomography and state engineering. Herewith, I would like to request Dr. Rajbir to start the seminar. Over to you, Dr. Rajbir.
Yeah, thanks for the introduction, Professor Manabendra. So I'm gonna share my screen now.
Hi Rajveer, how are you?
Good. How are you, sir?
Yeah,
Thanks
I'm good
for
to see
inviting
so
me.
many either Mohali speakers. So great.
Yeah. Yeah, thank you. Let me share my screen. Can you see my screen?
Yes.
Hello?
We can see.
Oh, you can see my screen. Yeah. Yeah.
Yes. 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 Please go ahead.
All right. Thank you to Professor Kavita Durai and Sandeep Goel for inviting me to this nice conference. Today I'll talk about new tools for quantum state tomography and state engineering. This work was done during my PhD at University of Virginia in Professor Olivier Pfister's lab. And here are my collaborators, Miller Eaton from Virginia, A. Lu Win and Carlos from Virginia as well, and Professor Myung-Sik Kim from Imperial College London, and Dr. Thomas Garrett, Adrian Lita, and Seunam from NIST. So here I'm gonna, oh, I can't go back. Right, I just wanna motivate, why do we want to characterize these complicated quantum state detectors and measurement, and the key advantage that we have in photonic quantum information processing that comes from having all these non-Gaussian resources. So for instance, last week, this paper was published in Science where, this is being weird. For some reason, my slides are moving by itself. All right, yeah, I hope this will work. So this week, last week, this paper showed up in Science where they achieved this computational advantage or the quantum supremacy on photonic quantum computer, where this is their experimental setup. So they essentially implemented Gaussian boson sampling with 50 squeezers and 100 by 100 interferometer, and then they sampled it using single photon detectors. So the idea to talk about this experiment is that now that we have officially achieved the quantum supremacy in photonics quantum computing, the community, the quantum optics community is pretty excited about it, and we'll see what comes next from such experiment. So now I'll give an overview of what it means to characterize quantum resources. So for instance, quantum state. So let's say you have a device that is generating these quantum state given by density matrix rho, and your goal is to estimate that. So the way this procedure works is you send these unknown copies, which are identically prepared, to a detector that is performing this informationally complete measurement. By that, I mean, you could use this measurement to completely estimate your density matrix. So how does that work? You find out the probability of having certain outcome that is given by Born rule, which is defined as this. So you send these unknown copies, and then you build your statistics for the different outcomes. And in this equation, there is only one unknown. So since you are doing the state tomography, you have the complete information about your detector POVM set, the measurement operators. So you can use some sort of numerical post-processing on your data to estimate your unknown quantum state. So what are these things we care about when we are doing such experiment? The first thing is that, is our reconstruction physical, in the sense that if we reconstructed a density matrix, does it correspond to a physical state, in the sense that, is it positive matrix, or is it normalized or not? Next thing is that if we are using some numerical post-processing on our data, is this computationally efficient and robust to the experimental noise? And if we have some losses that we can calibrate precisely, can we compensate for those non-losses? And in general, the quantum state tomography is hard because the size of the Hilbert space is exponentially large, so the number of measurement would be exponentially large as well, but sometimes the experimenter knows some prior information about the state. So how can we incorporate that information, and that allows us to reduce the number of measurement, and we are still be able to reconstruct the density matrix with the desired accuracy. And the last thing is that, do we have some technical limitation? For instance, if I'm doing state tomography using photon number resolving measurements, and if I have a detector that can only count up to 4 or 5 photons, can I use the detector to count to do a tomography for a state that has more than 5 photons? And if there are these limitations, how can we mitigate them? All right, so before I go into experiment, I'll quickly go over some notion of quantum optics. So if we quantize electromagnetic field, it turns out to be a quantum harmonic oscillator. So we can write down the Hamiltonian like this, and this is our good old Kirchner operator and the annihilation operator. And we can write down the quantized electromagnetic field, which is given as this. So similar to quantum harmonic oscillator, where we have position and momentum observables, we have amplitude and phase quadratures of electromagnetic fields. So these are, the straightforward analysis. And then we can also define the generalized quadrature, which is the superposition of Q and P, and this phi is the phase of the local oscillator. And I'll talk a little bit more about that. So this is, a Hermitian operator, hence an observable. So we can measure that in the lab, and we use balance mode detection to measure it. And I'll talk a little bit about it as we go further. So next thing is the representation. So classically, if you have a harmonic oscillator, the phase space would be an ellipse. And if you want to know where your system is, you just have to find out the coordinates. But in quantum mechanics, you could not measure Q and P at the same time. So you have to add the fuzziness around these coordinates, and you define the probability density. So for instance, this is the probability density in the position space. And then you can find out the average value using such formalism, right? Something we all are aware of. Then we can ask ourselves a question that can we define joint distribution function that we have in classical physics, such that if we marginalized over one variable, then we get our density in the other variable. So a function that has this kind of property. It turns out that we can define these functions, and thanks to Wigner, he defined those functions in 1932 when he was trying to understand quantum physics from a statistical physics point of view. So the Wigner function is uniquely defined for a quantum state, and it is an equivalent representation in the sense that all you know about your quantum state from the density matrix, Wigner function also has that information. So for a single mode quantum state, the Wigner function is given as this, and it has properties similar to classical distribution function, such that it is normalized over the entire phase space, and you can find your marginal for individual probability density functions. So this is nice, and we can also define these Wigner functions for quantum gates and measurement. So in principle, all you could do with density matrix, unitary gates, and doing these measurement POEMs, you could formulate the entire theory in Wigner function formalism. So that is nice, and quantum optics community use it a lot. So here are some examples of the Wigner function. So the first one is the vacuum state, the ground state of the harmonic oscillator or the electromagnetic field where we don't have any photons. The Wigner function is essentially a two-dimensional Gaussian Wigner function. And if we displace it, which is literally a displacement of this Wigner function in the phase space, we get a coherent state. So that Wigner function is still Gaussian, and this displacement is a linear operation. It does not change anything about your Wigner function. So this is still a Gaussian Wigner function because you have these, Gaussian nature. The third one is a single photon Wigner function, which is more interesting than the first two in the sense that it is non-Gaussian and it has these negative values around the origin of the phase space. So this is what really differentiates the Wigner function, the joint distribution functions, from classical joint distribution function, because in classical physics, you would not expect these negative values of your joint distribution function. And for this reason, these Wigner functions are rather known as quasi-distribution functions. So the last one is a Cat state. So you start with two classical states and you put them in the quantum superposition, and you see that your Wigner function has these negative features, which is what you would expect because it is a non-classical state now. So broadly speaking, you can categorize your optical systems in two states, Gaussian state with Gaussian Wigner functions and the non-Gaussian states. You could actually use the negativity of the Wigner function to certify that you have a quantum state. So if you are doing some experiment in the lab and you want to know that you have prepared a quantum state, you measure its Wigner function and you see it's negative, then you know that you have done something quantum. All right, so I want to emphasize on this operator, which is also known as displacement operator, which moves your Wigner function around the phase space given by the alpha, which is a complex number, so it has its phase and amplitude. So now next thing is the measurement. What kind of measurements we do to characterize this optical system? First one is the quadrature measurement, which is literally, what I said earlier, that these measurements are, the POVM is given by this set where x phi is the real number. And these measurements are Gaussian measurement in the sense that if you had Gaussian states, so for instance, vacuum or coherent state, the probability distribution for these measurements would be Gaussian distribution. On the other hand, these photon counting measurements are non-Gaussian measurements, and their POVM is given by this, where n is a natural number. So earlier I mentioned the informationally completeness of these measurements, and it turned out that these Gaussian measurements are informationally complete. You could use them to completely estimate your unknown density matrix. But if you are just doing photon counting measurements, you could not completely reconstruct the density matrix, and that can be seen from here. So if you measure photon number distribution of your quantum state, you can only measure the diagonal of this density matrix. But there are ways that you could use photon number resolving measurements and still be able to reconstruct these non-diagonal entries. But sometime, you have some prior information that the state you have is a Gaussian state, then you can actually use these measurements to completely characterize that. And this is recently published from Ayster-Mohali group. So this is an optimal scheme where you use these quadratic number of measurements to fully characterize Gaussian states and process as well. All right, so now I'll talk about this detector that we use to perform these photon number resolving measurements. So it is known as superconducting transition edge sensor. And it is essentially a superconducting sensor which is cooled down below its critical temperature. So if you look at the resistivity versus temperature curve, this is something we are familiar with. So if the photon gets absorbed, it increases the resistivity because of this linear sharp behavior. And the change in resistivity will change the current in this voltage bias circuit. And this change in current is being picked by this skewed electronics. So if you had 2 photons, then the change would be twice as much. And if you had 3 photons, it would be thrice as much. So if you send these pulses to a coherent pulses to a detector, then you can find out the probability distribution of these your coherent state. So as long as you don't go in this saturation regime, you can resolve your photon numbers. So the detector we have in Professor Olivier Pfister's lab at Virginia, it allows us to count up to 5 photons as 1064 nanometer, which is fine to characterize a state with weak photon number. So these detectors are the best PNR detector available today. They have near unity quantum efficiency and negligible dark count noise. And thanks to Seunam from NIST, we have one of them in Olivier Pfister's lab. So now how do we do the tomography for these optical systems? So the most commonly used technique is known as valence moment detection, where we simply interfere over unknown quantum state with a relatively strong local oscillator at a balanced beam splitter, and then we subtract the current from both of these photodiodes. So if you do a simple math, it turns out that this photocurrent, the subtraction of the photocurrent is proportional to the amplified value of your quadrature, your unknown quadrature. So it has been amplified by the strength of this local oscillator, which is a classical field. So what you do is you fix the phase of your local oscillator and you build your distributions for each quadrature. And those probability distributions are related with your density matrix as this and your Wigner function as this. So if you look at this integration carefully, your distributions are essentially the integration of your Wigner function projection on a plane that is defined by the local oscillator phase. So you can change the phase of your local oscillator and find out these different projections along all these planes. And then you use these computational intensive data post-processing, such as inverse transformation or maximum likelihood algorithm, to either reconstruct your density matrix or the Wigner function. And for Wigner function, those techniques were developed in 80s for medical imaging. So this is essentially a CAT scan where you simply measure your absorption spectrum at different angles and then use this post-processing to find out the image of the object you are trying to reconstruct. So these kind of scheme, they have been widely used and it works for small systems. But for instance, if you had a multi-mode quantum state, then you have to reconstruct these histograms for each of the mode. It can really get pretty complicated, and sometimes if you have some noise or low detection efficiency, it might even fail to converge. So it would be nice if you can avoid all this inversion process and directly reconstruct the Wigner function. And this is what I'll be talking next. So the idea was proposed in these 2 different papers where you have your unknown state and you interfere with a relatively strong local oscillator. And here you are modulating the amplitude and the phase. And your beam splitter is highly unbalanced. And then you are doing photon number resolving measurements. You don't care about this particular port of the beam splitter. So if you recall, this is essentially a displacement of your quantum state, an approximate displacement of your quantum state, right? So if you write down your Wigner function in this form, you can move your displacement in the beginning of the trace, and you can think it as expectation value of the parity over the displaced quantum state. And this parity measurements you can actually do using a PNR detector. So if you have alpha equals to 0, which is the origin of the phase space, your Wigner function is essentially, you find out the PNR distribution, you find out your average parity. So doing this, you can directly measure your Wigner function at the origin of the phase space without doing any numerical inversion using Redon transformation or maximum likelihood. You are directly probing that point. So now you might be wondering, how did this PNR measurement become informationally complete? And if you simplify this equation, you can write it as this. So now if you look at it carefully, you are doing displaced number state measurement, which are informationally complete. So they have phase as well as amplitude information. All right, so this is nice. To visualize it further, let's say we are trying to reconstruct the Wigner function of a single photon Fock state. So it is given as, this is the Wigner function. And if we did the parity measurement, we are directly probing this point, right? Now we displace it to a certain point and we are doing the PNR. We do the PNR measurement, we measure the parity, we are reconstructing this point. So by changing the amplitude and phase of the local oscillator, we can move this Wigner function over the entire phase space and probe it point by point, right? This is exactly what we did in this paper, where this is the reconstructed Wigner function for a single photon Fock state, and each black data point is the raw data point. We are not doing any inversion, we are not doing any post-processing on the data. So we displace it, measure the parity, plot it. So in the experiment, we change the phase of the local oscillator in 10 steps and amplitude in 20 steps, which is, the 10 different angular locations are for 10 phases, and these are different points. So we can clearly see that we have the negative Wigner function around the origin, which is what we expect, but we do not have the negativity of 1 over pi. And the reason for that is we have some losses in the experiment, which we can model it like this. So this is a single photon state, we displace it, and to model detection losses, we can put a fictitious beam splitter of eta transmission. So you can actually move these things around, and it turns out that both of these networks are equivalent as long as photon number distribution are concerned. So if you write down the density matrix here, this is what you have. So it's a mixture of a single photon and the vacuum. And the vacuum Wigner function is positive around the origin. So this positivity reduces the negativity of your single photon Wigner function. So, and that is why, if you want to directly probe the negativity of the single photon Wigner function, you have to make sure that your overall losses are less than 50%. Otherwise, you would completely lose it. And that happened to be the case in our experiment. It was about 58% efficiency. So to have a little discussion on this scheme, it is a direct reconstruction. We don't use any post-processing. We are directly probing the Wigner function by changing the phase and amplitude of the local oscillator and doing PNR measurements. So we have automated this entire process, so we can just do point by point for coherent state or vacuum state and things like that. There are some downside. The first one is that we are using this approximate displacement operation because we are implementing them using this highly unbalanced beam splitter. So that introduces some losses in the scheme itself, and your local oscillator is macroscopic. It's very strong compared to your signal. And if you had higher energy states, then you have to displace your Wigner function all the way until your Wigner function vanishes. And now you would need a detector that allows you to measure higher photon number, which is right now, all these transition edge sensor, they could count up to 17 photons. But if you want to characterize a state that has 50 photons, this scheme would not work. Another thing is that every time when you take your data, you are probing one point in the phase space. So if you had a Wigner function of a cat state, for instance, which is very complicated, the number of measurement to probe all these rich features in the Wigner function could be experimentally demanding. And if you had like a 2-mode cat state, then it can get even more complicated. And so far, we have not discussed anything about compensating for non-losses. So like if you had some losses, could you compensate and reconstruct a Wigner function as you expect? So in the next part of the talk, this is what we'll be addressing. So we propose this scheme, which is sort of a middle ground of balanced homodynamic detection and unbalanced homodynamic detection. So here, the scheme is the same. The beam splitter is balanced. So you do the same thing. You measure the parity, and it turns out that Wigner function at the origin of this mode is essentially the overlap between these two Wigner functions. So this is your local oscillator, your coherent state, and this is your unknown state. So you can write down these Wigner function overlap in the density matrix formalism. So this is something well known, and you can also do that for operators. So this is standard. So we measured the parity, hence the Wigner function at the origin. We can write down both of the unknown state and the coherent state in the photon number basis. Then this equation would simplify as this. And here I truncated my Hilbert space to n0 photon number for practical reasons, of course. So now I change the amplitude and phase of these coherent state and can reconstruct this matrix equation. So this is my data. These are different overlaps corresponding to different coherent state. These are the coefficient corresponding to these coherent state that I calibrate before doing the tomography. So I have complete information about this matrix. And the only unknown here is this density matrix for this unknown quantum state, which is written in the Liouville representation, where you simply stack all these rows in one big column. So we can write this equation in this compact form, and we can use this semi-definite program that has constraint that your reconstruction should be, your density matrix should be positive and normalized. So, and we minimize the L2 norm of this, this vector. So we went ahead and did some simulations for 2 states. The first one is a cat state, the second one is a GKP state. And these states are very crucial for continuous variable error correction and fault tolerance. So we did 400 overlap measurements, so 20 phase and 20 amplitudes of the coherent states. And we see that the fidelity for cat state is 1, and it's perfect reconstruction. And for a GKP state, it's about more than 98%. And the reason the fidelity is slightly lower here is because we probably need more measurements for a Wigner function that looks more complicated than the cat state Wigner function. So if you compare this scheme with the point-by-point reconstruction, in order to have a phase space resolution of this quality, you really need to probe it densely. So it could be very challenging, but here we can only do this with 400 overlap measurement. And such techniques have also been employed recently from NMR lab at ISR Mohali for NMR systems. So if you are interested, please go ahead and read this paper. So now the loss compensation that we haven't discussed yet. So to model losses, we simply put a fictitious beam splitter before a perfect detector, and we can write down the density matrix that has gone under these losses like this. So if you look at carefully, we can actually map it like this. So the diagonals of the loss degraded density matrix is they are linearly mapped with original density matrix using these upper triangular matrices. Their inverse is uniquely defined. So you could simply invert each of these maps to find out your original density matrix that has gone under some losses. So in principle, it works as long as you have a perfect reconstruction of rho prime. But if you had some errors in rho prime, then because of this analytical inversion, you could have some unphysical results, and which is what we see next. So here I did a tomography for a cat state with 50% losses using the scheme. And we see that the fidelity is only about 41 with a true cat state, and we do not see any phase space or the negativity of the Wigner function, which is something expected because cat states are highly sensitive to losses. So now if we use, so we know that losses are 50%. If we use those analytical inversion, this is what we would get. So we do recover the negativity, but looking at the photon number distribution, we have these negative values at higher photon numbers, which is not physical, right? And the Wigner function has all these weird ripples that is not expected for a single photon, for a cat state Wigner function. So to avoid these kind of instabilities in the inversion, we proposed this semi-definite program. So we minimize the L to norm like the previous one for each diagonal under these physicality constraints. And this one basically means that if you have some losses in the experiment, then your photon number distribution shifts towards low photon number. So that is also something expected. So if you use this SDP to invert for your losses, you see that your Wigner function is smooth and you don't have any negative probabilities. So your state is physical. And this is done in a single shot. So you reconstruct your loss degraded density matrix using whatever scheme you are using, and then you simply invert all of your losses in one go. So then we did an experiment for a coherent state and a single photon Fock state. So first I'll talk about the coherent state. So here we have the laser that gives us 1064 as well as 532. And 1064 is being used as a local oscillator. And since we are doing a tomography of a coherent state, we take a little bit of this coherent state in this path, and then we interfere at this beam splitter where we are doing the tomography. So to modulate the amplitude, we use this EOM along with a polarizer, and to modulate the phase, we use this piezo actuated mirror. So when you apply the voltage on this mirror, it moves back and forth. That introduces the phase shift. And then we combine the unknown state and the local oscillator at this beam splitter, and then the signal, the interfered signal, goes to the transition edge sensor through these optical fibers for photon number resolving measurements. And this is a single photon setup, so I'll talk about it in a little bit. So here is our single photon setup. So we simply pump a type 2 phase match OPO that has a PPK-TP crystal in it, and the cavity is designed at doubly resonance way. So these photons pairs are generated at half of the pump frequency, so 1064 nanometer, because that's where our local oscillator is. And these photons are generated in cross polarization because of this type 2 phase match. So we can separate them into different paths using this polarizing beam splitter. So when you have this OPO, when you have your crystal in an OPO, it allows for these other non-degenerate modes that are allowed by the OPO cavity. But we would like to prepare our photon pairs at half of the pump frequency. So we have to filter out all these non-degenerate modes. And to do that, we use this another filter cavity on the idler path. And the filter cavity and the OPO, both of them are locked at half of the pump frequency. So the filter cavity gets rid of all these non-degenerate mode. So this is the data. The orange one is what comes here after the filter cavity. So we see that it has less peaks because these photons have been filtered out. And this is the photon pair at half of the pump frequency that we care about. So we detect one photon here, and then this photon goes to the tomography scheme. So these are the results for a coherent state, which was a weak coherent state of 0.2 amplitude. And we take 60 overlap measurements. So we change the phase in 10 steps and amplitude in 6 steps. And the maximum amplitude of the local oscillator was only 0.3. So it's comparable to the original state we have, unlike the previous scheme where local oscillator is very strong. So these are the theoretical Wigner function and the density matrix, and this is the reconstructed one. So we see that the fidelity is near unity and it works pretty well. And now I'm going to talk about the result for single photon. So we had 50% losses in the experiment, and this is the Wigner function. So you don't see any negativity. And if you look at this density matrix, you have these known diagonal entries, which you shouldn't have because it's a state diagonal in photon number basis. But we have some noise in the experiment, and this is what causes all these known diagonal entries. Then we did the loss compensation using our semi-definite programming. So we see that the negativity of the Wigner function is recovered, and the fidelity with pure single photon Fock state is about 85%, and we still have these non-diagonal entries. So now I'm going to assume that the state I have is diagonal in photon number basis. That means my Wigner function should be rotationally symmetric. So that assumption allows me to phase average my data, and which is what I do next. And I use that phase average data for parity measurements, and we see that reconstruction is much better. That also means that the noise is coming from the amplitude noise of overlayer. So, and we don't see any non-diagonal entries, which is why the Wigner function is rotationally symmetric. So if we do the loss compensation of this reconstruction, it is nearly perfect. And if you compare that with the previous scheme where we could only probe the Wigner function until here because our detector got saturated, and the phase space resolution is much better compared to this guy. So here, the black data points are the raw data points, and the surface is the fit. So we see that we have the local oscillator, which is much smaller than what we had earlier. And we can construct the density matrix of the Wigner function over the entire phase space. So this scheme has this advantage that if you have a detector that saturates at low photon number, it allows you to still reconstruct the density matrix of the Wigner function. So that is nice. So to summarize this, we propose the scheme that guarantees the physicality. Since we are using this convex optimization, it is computationally efficient, and if we assume something about the quantum state, we can average the data that can make it robust to experimental noise. We are not using any approximation as we were doing in the previous scheme. And as I said earlier, that the demand for PNR measurement is not as strict as it is in the previous method. And here you can actually introduce well-calibrated losses and bring down the mean photon number of the state you are trying to characterize, because you know that your loss compensation works pretty well. So you can introduce well-known losses and then compensate for it. So that is also nice. It requires considerably fewer measurements compared to the point by point, because we saw for the CAT state and the GKP state. And we developed these techniques that are computationally efficient and allows you to compensate for your known losses or any other experimental imperfection in single shot fashion. So that summarizes the first part of the talk where we discussed about the state tomography. Now I'll move on to state engineering. How much time do I have?
You have about 5 more minutes to talk.
Okay, I think I can finish it, yeah. So now that we have single photons, coherent states, and photon number resolving measurements, what kind of other non-Gaussian state, which are crucial for all these quantum advantages in optical quantum processing, we can produce? So there have been several methods, both theory and experiments. So for instance, in this one, you added a photon to a coherent state. So the Wigner function of a coherent state is positive, but when you add a photon, you see that it has become negative, and it is not Gaussian anymore. This other scheme is where instead of having a beam splitter, you have a non-linear crystal. So you generate 2 mode squeezed vacuum and you detect n photon here. The other n photon have been added to the coherent state. So that's an n photon addition. The third one is the one we will be exploring, where you have a state. So for instance, a coherent state, and you interfere with an m photon Fock state. So for instance, for us, it will be m equals to 1. And you have this beam splitter that is also tunable. So you have a freedom on the amplitude of the coherent state, the parameters of your beam splitter, and the post selections for different PNR measurements. And it turns out that tuning these parameters, we can generate a variety of non-Gaussian states. So how does this work? So let's say we have our coherent state, which is written in the photon number basis as this, and we interfere with a single photon and we detect n photon here. So if you write down the wave function for phi b, it will be given as this. So if you look at this term, if you set nt square equals to Lr square, this term would vanish. That means in your original superposition, this L photon L fork component is not present after projecting it to the n photon fork state. So that is why it's known as fork state filtering. So a concrete example would be you have a coherent state of amplitude √5, single photon, balanced beam splitter, and you detect 2 photon here. So your original photon number distribution is Poisson distribution. And if you post-selected on 2 photons, this particular 2 photon component is completely gone. So if you look at the Wigner function, you had Gaussian Wigner function. Now it's non-Gaussian with negativity. So this is nice because it's a simple scheme and it allows you to generate these non-Gaussian states. So we can also tune these parameters. So here I'm tuning the alpha for a fixed value of n and r, and I can go from completely Gaussian to non-Gaussian states with increasingly Wigner function negativity. So if you look at this one, this is actually a perfect single photon fork state, which we could not do earlier because of this approximate displacement operation. And the reason it works is because if you look at the photon number distribution or the wave function of a displaced single photon state, it is given as this. And if you have m equals to beta square, then this particular component will be gone, which is what happens in the fork state filtering. So this allows you to generate a perfect displaced single photon state. So now we can think about iterating this process and see what kind of other non-Gaussian states we can generate. So the first one we'll be doing is the cat state. So there have been some methods both on theory and experiment. So the first one is you have a squeezed vacuum and you detect n equals to 1 here. This will generate a very weak coherence, weak cat state of amplitude 1.2 with fidelity 99. The other method is you have 2 single photons and you interfere them at a balanced beam splitter, but now you are doing a homodyne measurement at q equals to 0 that allows you to generate or approximate a cat state with amplitude 1.63 and fidelity of 99. So this is nice, but if you really want to do something with the cat state, as in you want to use them as qubits, or you want to use them as you want to use them for array correction, you need to have alpha greater than 2. So to do that, there have been some ideas. So this one is where you breed 2 small cat states. So you interfere 2 cat state at a balanced beam splitter, and then you do a homodyne measurement that increases the amplitude of your original cat state by a factor of √2. So if you want to do this, you would either use 2 squeezers or 4 single photons. But you can also use photon catalysis. So you have your coherent state with a single photon, do a PNR measurement, whatever comes goes to another beam splitter with another single photon PNR measurement, and you can repeat this procedure to generate these cat states. So for instance, here I've shown a 3-step process. So you have your original coherent state, you did your first PNR measurement, your 2 photon component is gone, but then you do it again with another freshly prepared single photon. Your distribution would look like this. And in the 3rd step, you have a weak coherence, weak cat state. So you see that it only has even photon numbers. To even go further, here I have shown, like, if you do it twice, you generate a cat state of amplitude 1.5 and your Wigner function look like this. So here is what we generate from photon catalysis. These ones are the theory one, and this is the difference. So just by using 3 single photons with in photon catalysis, we can actually generate a cat state of amplitude more than 2, which is nice because then you could do qubit encoding with that, and the fidelity is near unity. So if you want to go even higher, you can keep iterating this process. Although it would reduce your success probability, but it really depends on the application you have. Then we proposed a breeding protocol for GKP states. So in this paper, Vescancellos et al., they proposed that if you have 2 cat states and you interfere them at a beam splitter and you do a homodyne measurement, you can generate a square grid GKP state. In our work, we showed that you can actually do that with PNR measurements as well. And the PNR measurements are not only limited to 1, but you can have many of them. So here I've shown three different PNR measurements. The key difference here is that we have a phase shift. So you are essentially interfering two orthogonal Cat states. And the reason you have to do it because your photon number resolving measurements are phase insensitive. So that's why you have to account for that by introducing a phase shift before the interference. So this has fidelity more than 99 and the Gaussian width of 0.54. We can generalize this the PNR-based breeding protocol to any to increase the symmetry of any state. So here we have a state that has 120 symmetry in the phase space, and if you interfere two of them with a pi/3 phase shift, you can generate a hexagonal symmetry, and which is what also known as hexagonal GKP states. All right, with that, I would like to conclude my talk. We discussed two different continuous variable state tomography protocol with PNR measurements. We discussed producing these non-Gaussian states with single photon, PNR measurements, linear optics, and coherent states. And a simple extension to this single mode tomography we have been doing so far for single photon or a coherent state would be a two mode tomography for a two mode state. So you simply have two local oscillator, you interfere both of them, and you measure the joint parity of your two mode state. So this would be a straightforward extension. This work was supported by DARPA and NSF, and I would like to acknowledge my group, and I would also like to thank you all for your attention and organizers for inviting me, and be happy to take questions now.
Thank you very much, Dr. Rajveer, for this nice talk.
Thank you.
Now we are open for some questions, but I'm afraid we will not have much time. So maybe I will selectively choose some questions. So Arvind, you raise your hand. Could you please unmute yourself and place the question? Thanks.
Yeah, no. So I will not ask my detailed question. I just want to say that it was a nice talk, and also currently a lot of activity here. We are looking at many of the aspects that you talked about. One thing is that one of the major hurdles is to produce large amount of squeezing or a Gaussian state, which is kind of non-classical to a large extent. So are there breakthroughs coming in that arena where you can produce a very large amount of squeezing and so on?
Yeah, thank you for the question. That's a very interesting one, and that's what we want to do in order to have a scalable photonic quantum computer. So these days, there is this new platform, nanophotonic thin film lithium niobate, and that has strong nonlinearities compared to these bulk crystals such as PPKTP. And so far, there has only been, so the idea is to go integrated. So where you have the field confinement in a waveguide or a microresonator that allows you to enhance your nonlinearities. So in the bulk, the maximum squeezing has been achieved is about 15 dB, which is still not close to the fault tolerant threshold of 20 dB. But there is some room there. But having this thin film lithium niobate that has huge nonlinearities might help us get there. There are some challenges, and one of them is to go from chip to the free space. So you have these, Professor Das talked about the 6 dB losses. So if you have highly squeezed state, you are also more sensitive to losses. So there are challenges, but people have been working really hard. And my current work is actually to push that boundary where you could avoid these losses and measure your squeezing as you produce it.
Yeah, so we will have more discussions offline. Thank you.
Yeah, sounds great. Yeah, thank you.
Okay, so with this, I will take one more question. And so Chandan Sharma, can you please unmute yourself and ask the question?
Yeah, hello Rajveer.
Hi.
Yeah, these were interesting pieces of work. I have one question regarding the experimental implementation of the two outcome POVM. Let's say ket k bra k comma identity minus ket k bra k. So what is the limitations there? How much k can you reach? Like
oh yeah, so my POVM is not just two outcomes, I'm using the photon number resolving measurement. So it would be 0, 0, 1, 1, 2, 2, 3, 3, and so on. Right? If you had a click detector, that would have 0, 0 and identity minus 0, 0. But for me, it's PNR measurement. So I have 5 outcomes.
Okay, okay.
Yeah.
So can this POVM be implemented in laboratory? The two outcome like ket k brake that I mentioned. Ket k brake comma identity minus ket k brake. Yeah. Can this be implemented?
Yeah, people do that always. So this is essentially a single photon photodiode. So a diode, single photon avalanche photodiode. So you have this weak single photon, but it causes this avalanche in your semiconductor material that produces the signal that is above your electronic noise. So yeah, this is how you herald single photon.
Yeah, so you are able to, in your PNRD measurement, which is like ket 0, bra 0, ket 1, bra 1, you are able to go up to 5 photons or 6 photons, I don't know. So in here, the two outcome, let's say ket 10, bra 10, comma, identity minus ket 10, can I achieve such measurements?
So like when you say identity minus 6, bra 6 ket, what do you mean by that? So I understand the 6 bra 6 ket because that's a 6 photon detection.
Yeah, I know only the theoretical meaning. I don't know the experimental implementation.
Yeah, maybe we could talk about it offline.
Okay.
Yeah, I don't want to take the
but
yes, you can implement these POVMs. Yeah.
Okay, thank you. We can talk offline. Okay.
And
so thank you again.
Yeah, sure. I enjoyed reading your work on the Gaussian characterization.
Okay, thanks.
Yeah, of course.
Okay, we have one more question, but I will request Kate Preet to get in touch with Rajbir offline so that we save the time and keep our program on time. So with this, I would like to thank our speaker, Rajbir Nehra, for this interesting talk and also the discussion. So thank you very much, Rajbir. And with this also, I will go towards the last talk of this morning session. And our speaker is Professor Apurva D. Patel. Let me also introduce quickly our speaker. Dr. Apurva D. Patel is a professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore. He obtained his MSc in Physics in 1980 from the Indian Institute of Technology, Bombay, and his PhD in Physics again in 1984 from the California Institute of Technology, USA. He has extensively worked on lattice gauge theory investigations of quantum chromodynamics. His interest in quantum computation is mainly in algorithms and codes. So with this, I would request Professor Apurva Patel to start the talk. His title would be Understanding Quantum Chaos. Thank you very much. So it's over to you, Professor Patel.
Yeah, thank you for this invitation. Can you see my slide?
Yes, we can see it's not on full screen mode yet.
How do I magnify it?
Maybe you go to the view option. There should be some
view
presentation
is not
mode
showing up on the screen.
Does it work on Control
Alt L would do it.
Control L, no? Yes.
Alt L, Control L, I think. Yes. Yeah. Sorry.
So Control L might help. Yes.
Okay. So thanks for inviting me to give this talk. Remotely is all we can do these days. And I would take this opportunity to advertise a little bit about what we are doing here in addition to whatever I'm going to talk about. And that is at IISc, we now have a Center for Excellence in Quantum Technology. which is funded by MIT, and it is expanding with support from more sources. And hopefully we will be able to do many things in this center. Right now, the emphasis is mostly on reliably developing elementary hardware components which are needed for quantum technology. Okay, so now I can come back to the topic of chaos. What I'm going to talk about is quite straightforward, and so the talk will be pedagogical. But if you have any questions, you are welcome to ask me either in the chat box or at a later stage. So let me begin with a heuristic sense in which the word chaos enters our vocabulary, both in ordinary experience as well as in scientific terms. And in particular, in the scientific description, chaos appears in lots of places. It is underlying features like description of open quantum systems, irreversibility, approach to equilibrium, ergodicity, diffusion, randomness, and so on. And loosely speaking, it is showing up in two ways. Most of the time it is described as unpredictably of what is going to happen in the future, but it also covers the fact that we can't keep track of everything which has happened in the past. A lot of work has been done in this subject, both in the classical domain as well as in quantum domain. And I will briefly list few of the features which I'm not going to discuss at all. One of them is analysis of spectral properties of chaotic systems. They are described by what are known as random matrix theory, where the Hamiltonian is described in terms of each element being essentially random. And the main feature which appears in this theory is described in terms of the distribution of energy levels. In particular, chaos leads to what is known as level repulsion, and the dynamics described for regular systems have the distribution of energies going as Poisson distribution, which changes to a Wigner distribution for chaotic dynamics. And one can actually see this crossover by varying parameters in the theory. There is another way the density of states can be derived, and that is from recurrence analysis of periodic and closed orbits. And one can get a result which is known as the Gutzwiller trace formula. And the third aspect, which has recently become popular, is to look for various parameters of quantum information theory, for example, quantum discord, and use those parameters as a signature of transition between regular dynamics and chaotic dynamics. But I'm going to stick to something much more simple-minded than all these things, and that is the basic concept of how chaos is defined in the classical physics and how we can carry it over to the quantum language. So the standard definition of chaos in classical physics is that you start with two evolution trajectories which are very close by and let them evolve in time. And if the system is chaotic, these trajectories diverge very rapidly from each other. And this kind of divergence makes long-term prediction of a chaotic system unreliable when the initial data has limited precision. And a typical example quoted for this is the prediction of weather. Little bit of fluctuation in one place can change the whole dynamics of sufficiently long time in the future. And there are various quantified variables for this. The popular ones is a Lyapunov exponent, which describes how rapidly the trajectories move away from each other. Now let us go to the quantum domain. And this simple-minded definition doesn't work. Why? Because the common measure of distance between trajectories in quantum mechanics is a overlap or the dot product. In what sense? Is that we have states which are described by unit vectors. And if you take two unit vectors on a spherical surface, the distance between them two measured along the geodesic is just an arc of the great circle, and it measures the angle between these two vectors. The dot products will give you cosine theta, but cos theta is a monotonic function of theta for theta between 0 and pi. So it is as good. And so we can say that, okay, I'm going to characterize the distance between quantum states in terms of the overlap. But now if you take a genuine quantum system, all it can do is evolve by some unitary transformation. So psi will go to u times psi under some Hamiltonian. But the overlap of any two trajectories is invariant under unitary evolution, because in the overlap you will have u dagger and u coming next to each other and they just cancel out. And so this geodesic separation loses its meaning completely as a parameterization of the distance between two trajectories. And so the classical definition doesn't carry over. What should one do in such a situation? And that is why the examples I described in the previous slide, one go to a spectral description of chaos and tries to invent new parameters. But my point in this talk is, can we recover this classical description in a quantum system in a certain sense? And I'm going to argue that yes, we can. And that is achieved by looking at the quantum state, not as a unit ray in the Hilbert space, which is a familiar description, but as an analog of the phase space distribution of classical systems. So I'm going to go a little bit beyond the usual description. Not that the quantum state can be represented in phase space, that certainly can, but I'm going to say that the quantum state itself is a phase space. And that is a jump in the interpretation, which allows me to do something more. And then the invariance of the overlap under time evolution can be mapped onto something else, which is very well known in classical physics, and that the classical phase space under a Hamiltonian with a canonical evolution obeys the Liouville theorem, which says that the phase space density of states is invariant. So there is a invariant in the phase space. And so what does the Hamiltonian do? It doesn't change the density, but if you look at a little island in the phase space, the island can change its shape while the area remains fixed. And this is the analogy which I'm going to apply directly to what happens to a quantum state under chaotic evolution. So let me label the appropriate variable for this description, and that is the density matrix description of the quantum state. It's well known. It's a unique specification of the quantum state. It's Hermitian positive and has a unit trace. What it does is a generalization of the probability distribution of classical language to quantum theory, and so it can have elements, particularly the off-diagonal elements, which can turn complex. What is important for my purpose is that density matrix of any state carries with it a natural symplectic structure. And this symplectic structure allows me to look at the density matrix itself as a phase space. For example, the standard one-dimensional system, the differential geometry notation for this phase space is dx wedge dp, and for the Bloch sphere, it is d cosine theta wedge d phi. So the symplectic structure is well known. And now let me look at what happens to two nearby trajectories in terms of how this density matrix is going to change. So I take a unitary operator V, which separates one trajectory given by psi from another trajectory given by psi prime. And under time evolution, this operator V of t is a transformation of operator V at 0 by exponential of minus ist on the left and e raised to ist on the right. If I write this separation as exponential of some Hermitian operator O of t, then the differential equation for O of t is d by dt of O is minus I times the commutator of H and O. This equation is kind of well known, but I bring it out because it has the same form as the density matrix evolution in the Schrodinger picture, which is d by dt of rho t is equal to minus I times H commutator with rho. And I'm going to use this equation to make an analogy of how the trajectories separate with how the elements of density matrix are going to behave. There is more things known for this symplectic structure. I will point out one particular feature, that a pure state in n-dimensional Hilbert space is parameterized by 2n minus 2 real parameters. These are the elements of the density matrix. The two parameters which are eliminated, one of them is due to the normalization of the pure state, and another one is the overall phase of the state which is not observable. What is the count for the density matrix? That simultaneously measurable parameters of the density matrix are just the diagonal ones in whatever measurement basis you choose to adopt. And that number is n minus 1. 1 is removed because the trace of the density matrix is unity. And this n minus 1 is exactly half of the 2n minus 2 real parameters which are needed to describe the pure state. They are the labels for the generators of the computing Cartan subalgebra of SU1. And the other half is present in the description of the density matrix, but given quantum mechanics, you can measure only half of the parameters of a phase space. The other conjugate half becomes unobservable when you select a particular basis. It's just a uncertainty relation coming back in a different language. You can measure X, but then you cannot say anything about P. So these Cartan generators are fixed by the measurement apparatus. And I'm going to now look at what happens to these measured parameters as the density matrix evolves. The other parameters are there, but at any instant, I can measure only half of the parameters which are present. So in this framework, chaos is going to be characterized by a interplay between measurement basis and the evolution Hamiltonian. The Hamiltonian will change the diagonal elements provided it has some of diagonal elements. And if I'm going to label the diagonal elements by some operators of the measurement apparatus, the Hamiltonian will have to provide me the raising and lowering operators in that particular basis. I don't need any other distance measure. The intrinsic measure of the density matrix is sufficient for the purpose. And one side remark I can say, because it is familiar to all of us, that Wigner function, which is studied at least quite heavily in quantum optics, is nothing but the density matrix with the relative index Fourier transform. So what do I do? Well, I choose a basis. The diagonal elements are the measured quantities. The raising and lowering operators are conjugate to the diagonal ones. And another feature which turns out to be useful is the basis describing coherent states, because these raising lowering operators have a close connection to the description of coherent states. The coherent states are eigenstates of these raising and lowering operators in a certain sense. And this description carries over smoothly from the quantum region to the classical region if I use the coherent state basis by just varying the parameters of the coherent state labels. Now, what I can do is look at this density matrix evolution, and if I want to see the separation of trajectories, it is good enough to look at the linear response along specific generator directions, and that would allow me to identify chaos, and together with that, the relative rate of separation can give me some information about Lyapunov exponents, while the overall evolution still remains unitary. One feature which automatically appears in this quantum to classical connection is that classical state I can describe just as a single point in the phase space. But the quantum state has a minimal area in the phase space given by the Planck's constant for every conjugate pair of directions. So I cannot talk about just a single point. I have to talk about the evolution of this elemental area, and that is equivalent to smearing the classical description over this elemental area. And what it does, it removes small scale or high frequency fluctuations. And that is a language which is familiar to a certain extent in the description of coarse graining, which forms the foundation of the theory of renormalization group. So let me start now with simple examples. The first example I want to mention is a trivial one, the inverted harmonic oscillator. This example shows diverging trajectories, but there is no randomness in this divergence in any sense. The randomness will have to come from some new feature. What happens here is there is a local maximum in the potential, and you flow away from this maximum and you diverge in different directions. The Hamiltonian is just 1/2 of p square minus half of x square. And if you rewrite it in terms of the standard harmonic oscillator operators, that is proportional to a dagger square plus a square. And this can be easily recognized that it is a squeezing operator. The consequence of squeezing operator are well known, but in the language which I wrote down for the evolution dynamics, one can evaluate the commutators of this Hamiltonian with the phase space labels x and p, and that gives the equations that dx by dt is equal to minus p and dp by dt is equal to minus x. If you solve these equations, it's very simple. You get a general solution, which are hyperbolic functions with superposition coefficients, and the Lyapunov exponents turn out to be +1 or -1. The matrix in the linearized evolution can be written down as simple -1 on the off diagonal and 0 on the diagonal, and the determinant of this evolution, it's basically linear evolution, is 1. The phase space density therefore remains constant. And this language can be generalized to more complicated situations where the eigenvalues of m will become the Lyapunov exponents, and the corresponding eigenvectors will give the directions which expand or contract. And the scenario is actually very familiar in describing quadrature measurements in amplifiers using squeezed states. In these measurements, the focus is on reducing one of the dimensions of the quadrature to improve the accuracy, but at the same time, the orthogonal direction actually expands, and that expansion is the manifestation of chaos or diverging trajectories in this particular dynamics. One can include this dynamics in a normal oscillator by introducing a perturbation where you make the coefficient of x square and p square slightly unequal by perturbation, and then the perturbation Hamiltonian will be proportional to this inverted oscillator Hamiltonian, and then it will do the same type of evolution. And this is a very much feasible and realized practice in creating squeeze states. So now let me go to a little bit more complicated example, and that is a particle which is restricted to move on a circle, and chaotic behavior is created by giving it kick at some periodic interval. And the situation which I'm going to look at is actually very similar to that of a pendulum, where the Hamiltonian is half p theta square plus k times cosine theta. In my convention, theta equal to 0 is pointing up, and theta equal to pi is pointing down. And the kick is introduced by making this coupling k cos theta, which comes from gravity for a real pendulum, appear only for a short interval at t equal to n, and disappear in between these intervals. So this is a delta function gravity kick onto a pendulum in a simple-minded sense. The equation is very easy to integrate because all you have to do is alternate evaluation of theta and p theta. The point which is useful to note is that this evaluation has two fixed points. Theta equal to 0, which is pointing up, is an unstable fixed point like the inverted oscillator I described earlier, and theta equal to pi is an attractive fixed point like a regular harmonic oscillator. And in between, a lot of things can arise. The classical problem has been heavily studied, and it's known that for k greater than some threshold value, the system goes chaotic. The threshold value is about 0.97 something. So now let us look at the quantum problem. The evaluation equation for theta and p theta are straightforward. It's just a slight modification of the inverted oscillator, which I mentioned earlier. D theta by dt is a minus p theta, and d by dt of p theta is minus k sine theta times this periodic delta function. And the linearized evolution matrix can also be very easily constructed from them. It is off diagonal. One element is -1, then another one is minus k cosine theta times the periodic delta function. So this linearized matrix has both exponential and oscillatory modes. Which mode appears depends on the sign of cosine theta. If theta is in the upper half of the circle, cos theta is positive, and it has a growing mode like the inverted oscillator. And if theta is in the lower half circle, cos theta is negative, and there are only oscillatory modes. These are the two situations dominated by the two fixed points. And what happens between these two is dependent on the size of the kick, which is given by this parameter k. If k is small, then you are eventually always fall down to the lower half of the circle where there is an attractive fixed point, and you will just have a regular motion. But if the kick is large enough, then it will take you from the lower half of the circle to the upper half of the circle, and you will see the unstable growing mode, and the circle basically labels which half is chaotic and which half is regular. But there is something more that can be discerned inside this, and that is because the dynamics here is on a finite space. And in that finite space, something else shows up, and that is connected with the fact that on finite space, the eigenstates or the energy levels of the Hamiltonian are going to get quantized. They are not going to have continuous values. In case of this rotor, the eigenvalues are all well known. They are the orbital angular momentum values L, taking values in the set of integers, and in between values are not allowed. And what this does is you cannot have a state which is just a point on the circle. You have to have certain amount of smearing which is connected with the value of L, or rather the range of values of L that you can choose. And that smearing is a signature of quantum dynamics, or having a finite element area in the phase space. What does the smearing do? And it can be easily seen that under the smearing, the smeared values of cosine theta is less than cosine of the smeared values of theta. This is a typical example of a convex function where you average over a certain range the averaged value of the function and the average value of the parameter are connected with the actual curve of the function and the straight line segment connecting the two endpoints, and convexity gives that it always will be on one side of the value. And this averaging, when you apply to cosine theta in the unstable region, what it does is it reduces this size of the off-diagonal element. Cos theta now will become some effective value of cos theta, which is little bit less. And that reduction means that the rate of divergence of the trajectories, which is connected with the effective Lyapunov exponent, will come down when the state is smeared over a little interval of theta, which is a consequence of the discretized eigenvalues of the angular momentum. And this can be evaluated to a great precision, choosing specific values of L or even a distributions of L. That is because the evaluation operator can easily be written as alternative applications of this k cosine theta and half p theta square. And the p theta square is actually an eigen operator for both cosine theta as well as e raised to il theta. And so it can be just converted to a simple number. And what you find is you start with an e raised to il theta mode. It will evolve to e raised to minus ikt cosine theta plus il theta up to a position independent phase. So a generic function can be expanded in the basis of e raised to il theta, and you can see what happens to it under the evolution. And the result is that the expectation value of p theta square actually doesn't keep on growing as it does in classical physics, but it saturates at long times. This is the effect of smearing, and starting with values where the available range of L is limited, and see what happens in that particular case. So there is a quantum effect, and it always tends to cut down the chaotic diffusion. Allow me to go to a more complicated problem, and that is that of a kicked top, where dynamics is now in three-dimensional space. It is similar to this rotor, which is in two-dimensional space, but now we have the full angular momentum algebra, and we have to deal with that using the dynamics on the spherical surface, which is just a Bloch sphere. And this can be done for different values of the total spin S, and I'm going to describe how that can be done. Before that, I want to point out that it turns out that the case of spin half is rather special in this problem, because what happens is the algebra or the generators of spin half, the Pauli matrices, have a very simple relation that you multiply two of them, either you get the identity matrix or you get the third one. And for that reason, any generic Hamiltonian you can write down terminates at the linear term. You just cannot produce any higher order terms which give a different contribution. And so the Hamiltonian is up to a constant just n dot sigma, where n is some direction in the three-dimensional space, and all it does is make the spin precise around that direction. There is no chaos whatsoever. How do we see this? And for that, again, it's useful to use the coherent state language. I have written down one version over here, which is to take a completely symmetric state of two S particles, each particle having spin half. And that generates a state which is S with the third component of S also equal to the same value. And after that, you can rotate this state S comma S to any other direction by applying the standard rotation operator for the Bloch sphere, and it can be written down in terms of the components XX, SY, and SZ, and they obey all the standard angular momentum descriptions that we are familiar with. So in this language, now let me write down the kicked top Hamiltonian. It requires at least two terms, non-commuting operators, as well as non-linearity to be able to generate chaos. And the measurement direction I'm always going to take to be SZ, and the Hamiltonian I'm going to choose is some coefficient alpha normalized with various constant times SZ square, which is like the kinetic energy operator I was using earlier, plus a constant beta times Sx multiplied by a periodic delta function, and that is the kick part. So geometrically, this Hamiltonian represents two features. The kick is a rotation about x-axis by an angle beta. And the SZ squared term is actually a twist of the distribution around the z direction, because it represents the rotation angle about SZ, which itself is a proportional to SZ. So it literally twists in the opposite direction of the two hemispheres. And one can write down the Floquet Hamiltonian again, because the delta function part clearly separates from the rest, and one can write a product of two operators. So what happens, one can write down the evolution equations by evaluating the commutators of Hamiltonians. They are straightforward to work out, but they look too complicated and we cannot make any immediate conclusion from that. And it is actually helpful to go to the complex coordinates which are used in the coherent state description, familiar in quantum optics, but going back all the way to what Majorana did, and that is use this coordinate z, which is tangent of theta by 2 multiplied by e raised to I phi. The advantage of this coordinate is that all the SU2 eigenstates turn into monomials in this variable z. In particular, the state S and Sz is proportional to z raised to power s plus sz. And so any generic state you can take, you write it as a sum of the eigenstate. It will generate a polynomial in z, and the roots of these polynomials are what are known as Majorana stars on the surface of the sphere. And that's it. Those dynamics of these stars then describe how the evolution is changing as a function of some Hamiltonian. And one can actually write down the various spin operators as differential operators in this language. Yes, I will end in a couple of minutes.
Okay, thank you.
And that gives a simpler picture where the evolution can be written down as del z by del t as a commutator of h and z, and it ends up with two terms. One of them is proportional to z, and another is proportional to z square minus 1. A complete solution I have not been able to figure out, but I can see the solution of the two individual parts. The term proportional to z actually just produces a behavior like e raised to I, a constant times at t, which is a uniform rotation for z axis. And the term proportional to z square minus 1 produces a behavior that z is proportional to I times tangent of beta by 2 times n tau. This is nothing but the definition of z itself showing up in a different form. It has the same function of tangent theta as a radial magnitude. And so what happens in the evolution is basically a spiral. You rotate by some angle and then give it a kick in the radial direction, because this second half just changes the value of z in the radial direction. And that is how the diverging trajectories appear, by a spiral which keeps on growing as a function of time, and then it becomes reflected back after the time hits a multiple of pi by 2, etc. But something else automatically appears, that if you don't have the mixing between these two quantities, you will have no chaos. And that can be written as a multiple of the coefficients which are appearing over here. And that condition is alpha times beta times 2s minus 1. And mysteriously, this factor 2s minus 1 has appeared from the algebra, which says that if s is equal to half, there is no chaos. What has happened here is actually a consequence of the phase space smearing. For s equal to half, there are only two states on the Bloch sphere. So the smearing is as large as the hemisphere itself. And this volume is so large that any diffusion which is produced by other terms, you smear it, it completely gets wiped out, and you have no noise left. So this is the result for the kick top, and my time is now up, so let me just put up the summary. one can look upon the chaos as an evolution of the density matrix itself, as an analog of the phase space dynamics. And this is much easier to analyze than spectral signatures. There is a minimal area in the phase space, which is Planck's constant for each conjugate direction, and that wipes out small scale fluctuations from the evolution. And this separation of diffusion, the classical chaotic diffusion, has an analog in quantum theory in condensed matter physics. It is known as Anderson localization. The states don't wander arbitrarily, they get localized, and this indeed happens for a single qubit. You do not have any chaos left at all, and that is the state with the largest area in the phase space. If you decrease the area, you will gradually move towards the classical region where chaos starts appearing more and more prominently. And you can look at as whatever, an understanding of crossover between classical and quantum region. Thank you very much.
Thank you very much, Professor Patel. We have a question. Well, we have time for one question. Yes, I see Professor Arvind. So Professor Arvind, can you please unmute and place the question?
Yeah. Apurva, thanks for a detailed pedagogical talk exposing the ideas in quantum chaos from a very new and different perspective. Thank you for that. I have two questions. Number one, you see, can one actually get the classically chaotic trajectory as a quantum limit of something? Maybe that's my second question. My first question is directly related to your talk, and then this is the second question. The first question is the signatures in terms of spectrum and signatures that which you are finding, do they have a complete correlation that when one is found, the other is also found? And my second question is there a way of getting the classically chaotic trajectories as quantum limit of certain trajectories in Hilbert space?
There is a one-to-one correspondence between this phase space description of the density matrix and whatever happens in the quantum world. That is in the sense that the density matrix contains everything which has to be known about the quantum state. All which is needed to map to the quantum, for the classical region, is take a initial state which is genuinely quantum. And that is where the smearing picture appears. You cannot have just a point, but you have to define a genuine quantum state, which is a little bit of elemental area, and then ask the question, how is this area going to evolve under time? And that smearing actually produces an effect, wiping out some of the high frequency fluctuations. And that is my understanding of how well the classical and quantum regions can be connected. The situations which can be chaotic in the classical region will turn less chaotic in the quantum region because of this smearing. And a single qubit is an explicit example where chaos just disappears, or rather, it's not possible to have chaos.
Okay, thank you. So I see one question coming from Professor Arul. So if the question is short, please keep it. Otherwise, I will request you to directly contact Professor Patel. Yes, please.
Okay, I don't know if the well, maybe the question I can keep it short. Apurva, you say for the kick top, by your definition of chaos, there isn't one for S equals half. But even if you look at S's 3 halves, it's really just a kicked, a transverse field Ising model, which is actually integrable. So I think the issues of chaos in a finite system is much more, nuanced. And so that's one of my comments. The other one is I'm not very sure I understood the new content, because of course, I mean, the localization in the kicked rotor is also well known. So can you just please, I think I will just cut short with that questions. Yeah, thanks, Apurva.
Yeah, the new content is limited in the sense that I'm using all the well-known machinery and results which are there in the literature. The only content I'm trying to add is use a new phrasing or a new language about how one should look at this picture. And probably that is my hope, that it will allow us to understand finite dimensional systems better than what we have been able to do so far.
Okay. Thank you.
So thank you very much, Professor Patel, for this interesting talk and also the discussion. So with this, we are about to close our first session of the day. And with this also, I would like to take the opportunity to thank all the speakers, all three speakers of this session for these interesting talks. So with this, we close the session here. Our next session will start at 3 p.m. Indian time today. Thank you very much, everyone. Thank you very much.